Okay, so we're looking at the backside of a thermodynamics cycle for a class example. I forgot to record the first side, so here's the back. We are looking at this triangular graph here. It's going in a counterclockwise direction, or anti-clockwise. And what we are just asked is, what is the name of the thermodynamic process as the gas goes from point B to point C? And that really doesn't make any sense because it's not going from point B to point C. It's going from point C to point B, but potato, potato. So what is that? That's an isobaric, right? So this is an isobaric or an isobar. Our pressure is staying constant there. Our pressure is at 1 kilopascal. So that's like 1,000 pascals or 1,000 newtons per meter squared. Okay, so be careful about those units on the axes. When we go from C to A, or rather A to C in this example, that is the vertical line right here. What is that thermodynamic process? That's an isochoric or an isovolumetric. Depends on how your professor decides to talk about that. And then if we wanted the network done as we go A to C to B and then back to A, if we make the whole loop, how would we go about finding that network? That's normally our area under the curve, or since we have a full cycle here, we can just look at the area of our triangle, right? So as long as we get that area of the triangle, we will be set. That is like all of the areas under the curve for positive and negative amounts. When we do this, since it is a nice right triangle, which will be the only things we see in the AP2 class, we'll have triangles and squares. If there is a weird function, they have to like give you a lot of information about it already. So we'll see in terms of getting areas, easy shapes. But that's just a classic 1/2 base times height. Our base here goes from 4 to 10, so that's really a value of 6. So we've got 1/2 times 6. And then our height goes from 1 to 5, so that's really a value of 4. And then technically speaking, it's 4,000. So this is going to be 6 times 4 is 24, divided by 2 is 12, 12,000. That's 12,000 joules, or you could write that as 12 kilojoules. However you'd like to do that. But no matter what, that work is the area. So the question now becomes, is this work being done on the system or by the system? Sending it back to Gio.
It's being done on it because it's positive.
Gio says work is being done on it because it is positive. Gio, here's my counter argument to you. I'm not saying if you're right or wrong, but I'm saying we define if it's positive or negative based on if the work is being done on or by the system. Or by or on, vice versa. So you made a circular argument there.
Okay. Well, so it would be, so if the work done is negative or positive.
So what we do indeed have here is, because this is going in this counterclockwise, anti-clockwise fashion, we have a work being done on the system. You know, we're kind of collapsing our volume here. We call that for us a positive work, but you know, if you're using a different convention, it is what it is. Okay. If we look at the next one here, number 17, if 20 kilojoules of thermal energy is entered into the system, shown above in this PV graph, what is the change in internal energy of the cycle? So if we're looking for a change of internal energy, we're looking for a delta U. Now, our first gut might be to look at temperature changes and do a 3/2 NR delta T. But in this case, we're given energy entered into the system. We know that that 20 kilojoules there, that is Q. And since it's entering into the system, that is a positive value. So we're going to get 20 kilojoules, and then the work that is done here, which is going to be another 12 kilojoules. Okay, if we want to just find temperatures at specific locations, if the process occurs to a system containing 4 moles of gas, then what's the temperature at location B? We know that temperature given by PivNert, or PV equals nRT, we can say temperature equals PV over nR. We know the pressure at point B is 1,000, so this will be 1,000. We know the volume is 10, and then divided by 4, because of 4 moles. And then our R value here for our SI units is 8.pi, or 8.314. So that'll be 10,000 divided by 4 gives us 2,500, and then divided by 8. Oh, that's going to be a weird kind of number there, isn't it? Yeah, but it should be about 300. And that's 300 Kelvin. We are in kelvins for those values. For the delta T's, we don't care about Kelvin and Celsius, but we're looking for temperatures in and of themselves. They're going to come out as Kelvin. If the process occurs to a system containing 4 moles of gas, then what's the change in internal energy during the process from A to C? Well, to do this is actually going to be a little bit of work for us. No pun intended. From A to C, there is no work done here. So what's an easier way to do this problem is to actually use the delta U equation. Delta U equals 3/2 nR delta T. That is the Leo, Dinch, Augie equation, the lad. But in order to do this, we need the 2 delta T's, which means we need to do this PV over nR for both of the initial things. Let's just do this off to the side here. Temperature at A is going to be 5,000 times, oh, what's that volume there? 4? Could I just cancel out the NR? Yeah, I could. The NRs are just going to go away. So I could just say here that this is like the delta A and the delta C, or the TC here. It's just going to be PV and PV again, because the NRs in this equation are going to die out. So that's going to be, what, 20,000? And then the PV for TC is going to be 4,000. And then since it's final minus initial, it's going to be 4,000 minus 20,000 for 16. Well, negative 16,000. And then 3/2 of that, right? Pause this. We did a bunch of work on the side, but then we came back, and then whenever you do it all, you get the following. You get about negative 24,000 joules. You can either find the temperatures of TC and TA. TC is 120, TA is 600, and then do that, or you can do this little neat algebra over here and just call it a day. Anyways, that's what you get. Whew. Okay, how much work is done on the system, or done by the system, going from C to B? That's just the area underneath here. So a base of 6 and then up of 1,000. Look at that. It's 6,000. And since this is increasing the volume, we can say this is work done by the gas or by the system. And we did that just by finding the area of this rectangle down here. Base is 6 because 10 minus 4 is 6. Our height is 1 because we only go up to 1. If we do the same thing from B to A, we're going to have a slightly different shaded region. We're going to have the 6,000 from down here, but then we also have this triangle, which, kudos to us, we already know what the value of that triangle is. We already worked out previously that it was 12. So that triangle's 12. We have an extra 6 in the bottom there. 12 and 6 is 18. And that's going to be done on the system, or on the gas. Because we're going to the left there, our volume is decreasing. And then last but not least here, how much thermal energy is added or removed from the system from C to B if this process occurs to a system containing 4 moles of gas. In this case, it's very similar to what we did on the front side, but because that video doesn't exist, what we can actually do here is we can do the delta U equals 3/2 NR delta T thing again. When we run this, our two temperatures here are going to be 300 minus 120. That is the temperature of B and the temperature of C. And when we do this for the 4 moles of gas and the 8.314, we're going to get a delta U of 9,000 joules. So when we go ahead and use the first law, delta U equals Q plus W. What we're going to find here is we're going to have 9,000 joules, or I can just write it as 9 kilojoules, equals Q, that heat that we're looking for, either added or taken away from the system, and then the amount of work done on or by this system here. So that should be the, what did I have? That should be, where's C to B? That's 6. I'm looking at my numbers here. There's so many numbers on this page. And then, whoop whoop. Q equals 3.
Although wasn't the 6 negative?
Yeah, it's done by the system.
Ho ho!
Whoa!
That 6 is negative. So here, let's erase this and then talk it so I think it records right, because I don't think I'm recording for some reason right now. Oh no, I am recording. Hello! This is all messed up. Sorry, future. So we got the 9 kilojoules from up here. This equals Q. We add the work in from C to B. That's 6,000 or 6 kilojoules, but it's done by the gas. So it's a negative value. So we've got ourselves a negative 6 kilojoules here, which means we want to find Q. We add the 6 over, and that gives us 15 kilojoules. That negative right there, that's the doozy. That is the doozy. And if we were recording through all that, we saw us make the mistake, then we saw we were recording, then we came back and we fixed it. Okay? So be careful about the big doozy steps. Stuff you don't want to mess up. Okay? Hopefully, this recorded right and everything in here made some sense as an example. If you had no idea what we did here, go back and watch the first law examples that we've done and just look into the first law in and of itself. But this is finished. Adios. Take it easy.